Picture this. You're standing in one of the most geologically violent places on Earth. The ground beneath your feet shifts constantly. Earthquakes strike without warning. Typhoons tear across the landscape. The air is thick with humidity that rots wood and rusts metal. Now imagine you need to build a house here. A house that will protect your family. A house that needs to last for generations. But here's the catch. You have no steel, no concrete, not even nails. Impossible, right? Wrong. Because while the rest of the world was building structures designed to resist nature's fury, one civilization figured out something far more brilliant. Don't fight the earthquake. Dance with it. This is the story of how ancient Japan solved one of engineering's most brutal challenges with a solution so elegant, so counterintuitive, that modern architects are still studying it today. A solution built entirely from wood, geometry, and centuries of hard-won wisdom. Let's dive in. The invisible enemy. To understand why Japanese architecture evolved the way it did, you need to understand the nightmare Japan lives with every single day. Japan sits on the Pacific Ring of Fire, where four massive tectonic plates collide in a geological demolition derby. The Pacific Plate, the Philippine Plate, the Eurasian Plate, the North American Plate, all grinding against each other beneath Japanese soil. The result? Japan experiences over 1,500 earthquakes every year. That's 4 earthquakes every single day. Most are minor tremors, barely noticeable. But some are catastrophic, history-changing, civilization-ending, and it's not just earthquakes. Typhoons barrel across the islands with terrifying regularity, bringing winds that can tear roofs off buildings and rainfall measured in feet, not inches. The humidity is relentless, creating the perfect environment for wood rot and decay. This is the environment ancient Japanese builders had to work with. Now, here's what most people get wrong about earthquake engineering. They assume the solution is to build stronger, thicker walls, heavier foundations, more rigid structures that can withstand the shaking. That's exactly backwards. Because here's the brutal truth about rigid structures in earthquakes. They don't bend, and what doesn't bend breaks. When an earthquake hits, the ground moves. If your building is locked rigidly to that ground, it has no choice but to move with it. All that kinetic energy transfers directly into the structure. Walls crack, joints fail. The whole thing comes apart. The problem isn't the force. The problem is fighting the force. And that's where the Japanese made their genius leap. What if we stopped fighting? The Japan of the samurai. To understand Japanese architecture, you need to understand the culture that created it. This was the Japan of the samurai, a society built on discipline, precision, and an almost obsessive attention to economy of movement and resources. Nothing was wasted. Every action had purpose. Every tool had meaning. The samurai's relationship with the sword wasn't just about combat. It was about understanding materials, leverage, balance, and the subtle interplay between rigidity and flexibility. A sword that's too rigid shatters. A sword that's too flexible bends uselessly. The perfect blade has just enough of both. This same philosophy extended to carpentry and architecture. In feudal Japan, wood was the foundation of everything. Temples, houses, castles, bridges, all built from timber. But this wasn't a limitation. It was an opportunity. Japanese craftsmen didn't just work with wood, they understood it. They knew how different species behaved under stress. They knew how grain direction affected strength. They knew how to read the subtle variations in color and texture that indicated structural integrity. The swordmaker, the carpenter, and the architect weren't separate professions. They were all students of the same fundamental principles, working with natural materials, respecting their inherent properties, and finding strength through flexibility rather than brute force. The house wasn't just a structure. It was an extension of this philosophy, a living thing that breathed with the seasons, moved with the earth, and survived through adaptation rather than resistance. The foundation that refuses to fight. Let's start with the most counterintuitive decision in Japanese architecture. The foundation that isn't really a foundation. In Western construction, you anchor your building to the earth. You dig down, you pour concrete. You create a rigid connection between ground and structure. The building and the earth become one unit. Japan said, absolutely not. Instead of fixing the house to the ground, Japanese builders placed wooden pillars on top of large, flat foundation stones. That's it. No anchors, no concrete, no rigid attachment. The house literally sits on the stones. It's not bolted down. It's not cemented in place. It's just resting there, and it's elevated. The floor of a traditional Japanese house sits several feet above ground level, creating an air gap beneath the structure. Sounds insane, right? Your first instinct is probably that this house would slide right off its foundation during the first tremor. But here's what actually happens. When an earthquake strikes, the ground moves violently. Those foundation stones move with the ground because they're part of it. But the house can slide slightly on those stones. It can shift. It can move independently from the earth beneath it. Instead of the earthquake's energy transferring directly into the structure and tearing it apart, The structure absorbs that energy through controlled movement. It's not fighting the earthquake, it's floating above it. Think of it like this. Imagine you're holding a tray of glasses during an earthquake. If you grip the tray rigidly and move exactly with the shaking, those glasses are going everywhere. But if you let the tray move slightly in your hands while keeping your arms flexible and absorbing the motion, the glasses stay put. That's what a Japanese house does. It lets the foundation move while the structure above dances with it, absorbing energy instead of fighting it. A house that's bolted down has nowhere for that energy to go except into structural failure. A house that's free to move dissipates energy through motion. The elevated design has another benefit: protection from moisture. By keeping the wooden structure off the ground, air can circulate underneath, preventing rot and extending the life of the building. One simple decision: don't anchor the house, solves two problems at once: earthquake survival and moisture management. The skeleton that bends now. Let's look at the structural system itself. The skeleton of the house. A traditional Japanese house is built around a post and beam framework. Vertical pillars support horizontal beams, creating a grid-like skeleton that carries all the building's weight. But here's the critical part. This skeleton is designed to flex. The pillars aren't massively thick. The beams aren't over-engineered. Everything is precisely dimensioned to be strong enough to carry the load, but not so rigid that it can't move. When an earthquake hits, this framework doesn't try to stay perfectly still. It sways. The joints between pillars and beams allow for subtle movement. The whole structure absorbs the earthquake's energy by deforming slightly, then returning to its original position. Think of it like a human skeleton. Your bones are rigid, yes, but they're connected by joints that allow movement. When you stumble, your joints flex and absorb the impact. If your skeleton was one solid, rigid piece, you'd shatter. A Japanese house works the same way. It's a collection of rigid elements connected by flexible joints, creating a structure that's both strong and adaptable. Compare this to modern reinforced concrete construction. Concrete is incredibly strong in compression, but it's brittle. It doesn't flex. When stressed beyond its limit, it doesn't bend, it cracks. Those cracks propagate rapidly, and the structure fails catastrophically. A wooden post and beam system, by contrast, can deform significantly before failing. Wood is surprisingly flexible. It can bend, compress, and twist while maintaining structural integrity. Even if individual members crack, the distributed nature of the framework means failure happens gradually, not all at once. The weight distribution is crucial too. In a Japanese house, the load is spread evenly across many pillars. No single point carries too much stress. If one pillar is damaged, the others can compensate. This is structural redundancy at its finest. Not through massive overbuilding, but through intelligent distribution of forces. Shot without nails, without cement. Here's where it gets really impressive. Traditional Japanese carpentry doesn't use nails, or screws, or metal fasteners of any kind. Nothing is glued, nothing is cemented. The entire structure is held together by wood alone. How is that even possible? The answer is joinery. Specifically, a system of interlocking wooden joints so precisely crafted that they lock together through geometry alone. Let me explain why this matters. Metal fasteners seem like the obvious solution for connecting pieces of wood. Drive a nail through two boards and they're connected. Simple, right? But there's a problem. Metal and wood behave differently. They expand and contract at different rates with changes in temperature and humidity. In Japan's climate, with hot, humid summers and cold winters, this creates a constant cycle of expansion and contraction. When metal is embedded in wood, this differential movement creates stress points. The wood around the nail weakens over time, especially with the constant vibration from earthquakes. Those connections loosen. The nail doesn't hold as well. Eventually, it fails. Worse, metal rusts. In Japan's humid climate, rust happens fast. Rusted fasteners weaken further. They expand, splitting the wood. What was supposed to hold the structure together becomes a point of failure. So Japanese carpenters eliminated metal entirely. Instead, they developed joint systems based on three principles: geometry, compression, and friction. Take a mortise and tenon joint, one of the simplest examples. You cut a rectangular hole, the mortise, in one piece of wood. You shape another piece to have a matching rectangular projection, the tenon. Slide the tenon into the mortise, and the two pieces lock together. But Japanese joinery goes far beyond simple mortise and tenon. They developed hundreds of joint types, each optimized for specific structural situations. There are joints that lock through wedge action, where the act of pushing the pieces together creates compression that holds them in place. There are joints with multiple interlocking surfaces, creating such complex geometry that they can't come apart without being disassembled in a specific sequence. There are joints that use the building's own weight to strengthen the connection. Here's the brilliant part. Many of these joints get stronger under load. When weight presses down on a properly designed joint, it creates compression that forces the interlocking surfaces more tightly together. The heavier the load, the tighter the joint. The structure literally holds itself together through its own weight. During an earthquake, when the building flexes and moves, These wooden joints can deform slightly without breaking. They absorb energy through friction and compression. Unlike a rigid metal connection that either holds or fails, a wooden joint can yield, absorb stress, and return to its original position. This is resilient engineering, not rigid, not brittle, adaptive. And here's something most people don't realize. These joints were invisible. In a finished building, you couldn't see them. Craftsmanship was hidden inside the structure, known only to the carpenter who created it. This wasn't just engineering. It was art. An entire language of structural problem solving, encoded in wood, passed down through generations of master carpenters. Walls that don't hold anything up. Now we get to another counterintuitive feature. The walls. In most architecture, walls serve two functions. They separate spaces, creating rooms and privacy, and they hold up the building, carrying structural loads from the roof down to the foundation. In a Japanese house, walls do exactly one of those things. The structural framework of pillars and beams carries all the weight. The walls? They're just space dividers. They don't support anything. Traditional Japanese interior walls are called shoji and fusuma. Shoji are wooden frames covered with translucent paper. Fusuma are wooden frames covered with opaque paper or fabric. Both are incredibly light. You can lift them with one hand, and both are removable. They slide on tracks. You can reconfigure entire rooms by moving walls around. Why would you design a house where the walls are basically decorative screens? Two reasons. First, flexibility. In feudal Japan, houses needed to serve multiple purposes. During the day, you'd slide the walls to create large open spaces. At night, you'd rearrange them to create smaller sleeping areas. Different seasons, different activities, different configurations. But second, and this is crucial for earthquake survival, sacrificial components. During a major earthquake, things break. That's unavoidable. The question is, what breaks, and does it matter? In a house where the walls carry structural loads, wall damage means structural damage. The building's integrity is compromised. In a Japanese house, wall damage means you need new paper screens. That's it. The shoji and fusuma are designed to be damaged. They're meant to tear, to break, to absorb energy by failing. But because they're not structural, their failure doesn't threaten the building. After an earthquake, you might have torn paper and broken frames, but the house is still standing. The framework is intact. You repair the walls, a task that takes hours, not months, and life continues. This is damage control through intentional weakness. You make certain components deliberately fragile so they fail first, protecting the critical structural elements. Modern engineers call this a fuse system. You design specific parts to fail predictably under stress, dissipating energy before it reaches components you can't afford to lose. Japanese carpenters figured this out centuries ago, without computer simulations or engineering degrees. They did it through observation, experience, and an intuitive understanding of how structures behave under stress. The roof's paradox. Let's talk about the roof, because this is where Japanese design makes another fascinating decision that seems to contradict basic engineering. Japanese roofs are big, really big. They extend far beyond the walls of the house, creating wide eaves that can overhang by several feet. They're also heavy. Covered in ceramic tiles or thick thatch, these roofs add significant weight to the structure. Common sense says, keep the roof light. Less mass means less force during an earthquake. Every engineering student learns this, but Japan went the opposite direction. Why? Because they were solving multiple problems simultaneously. Those wide, overhanging eaves serve a critical function: weather protection. Remember, Japan gets hammered by typhoons and heavy rainfall. If rain hits the walls directly, the paper screens get destroyed. Wooden components rot. The building deteriorates rapidly. But if the roof extends several feet beyond the walls, it creates a protective umbrella. Rain falls harmlessly to the ground, never touching the walls. The eaves also provide shade during hot summers, keeping the interior cooler. So the wide roof solves climate control and weather protection. But what about the weight? Here's the trick. The weight is part of the structural system. That heavy roof pressing down on the post and beam framework creates compression in the joints. Remember those wooden joints that get stronger under load? The roof's weight is what activates them. Additionally, that mass creates inertia. During minor earthquakes, the constant tremors Japan experiences daily, the roof's weight keeps the building stable. The structure beneath can flex and absorb the movement, while the heavy roof stays relatively still, acting as a damper. It's only during major earthquakes that this becomes a liability. And Japanese builders knew it. That's why the roof isn't rigidly attached. It sits on the framework, yes, but with some give in the connections. If the earthquake is strong enough, the roof can shift slightly without tearing the entire structure apart. And if disaster does strike, if the house collapses. Those ceramic tiles are salvageable. The wooden beams can be reused. Even in catastrophic failure, the materials have value for rebuilding. The philosophy beneath the structure. We need to talk about why all of this exists, because Japanese architecture isn't just clever engineering. It's a physical manifestation of a completely different worldview. Western architecture, particularly after the Romans, has been obsessed with permanence. We build monuments meant to last forever. Concrete structures designed to resist time itself, buildings that declare, we will not yield. The Japanese approach is fundamentally different, rooted in concepts that seem almost philosophical, but have direct engineering implications. First, impermanence. In Japanese culture, nothing is meant to last forever. The most sacred Shinto shrines are rebuilt every 20 years using the exact same techniques, the exact same materials. This isn't because they've degraded, it's intentional. It's ritual. The act of rebuilding passes knowledge from one generation of craftsmen to the next. The shrine is reborn, and the tradition is kept alive through practice, not preservation. This acceptance of impermanence changes how you approach construction. If a building isn't meant to last 1,000 years, you optimize for different things: adaptability, repairability, material efficiency. You don't over-engineer. You don't build thicker and heavier just to add decades to the lifespan. You build exactly as much as you need, knowing that when the building does eventually fail, you'll simply build it again. Second, flexibility over strength. There's a famous concept in East Asian philosophy, often illustrated by the story of the oak and the reed. The mighty oak stands rigid and proud. When the storm comes, it refuses to bend. The wind snaps it. The stubborn oak falls. The reed, thin and flexible, bends with the wind. When the storm passes, the reed springs back up, unharmed. Japanese architecture is the reed. It doesn't try to overpower nature. It doesn't try to create an immovable object that can withstand any force. Instead, it moves with nature, absorbs the energy, and returns to equilibrium. This isn't weakness. This is sophisticated understanding of force dynamics. Third, accepting disaster as inevitable. When you live in a place where earthquakes happen daily and catastrophic ones strike every few decades, you can't pretend disaster won't happen. You can't build with the assumption that if you just make it strong enough, you'll be safe. Disaster will come. The question is, what happens after? Japanese architecture is designed for the aftermath. It's designed to minimize casualties when things go wrong. It's designed to be repairable. It's designed so that the community can rebuild quickly and move forward. The house isn't a fortress meant to protect you from nature's wrath. It's a shelter that keeps you safe during the ordinary days and gives you the best possible chance during the extraordinary ones. And if it fails, you rebuild, because you always rebuild. This might sound fatalistic to Western ears, but it's actually deeply practical. By accepting that disaster is part of life, you can plan for it rationally, instead of pretending it won't happen. When the house falls. Let's talk about what happens when everything goes wrong. Because it does. Throughout Japanese history, massive earthquakes have leveled cities. The Great Kanto earthquake of 1923, the Kobe earthquake of 1995, the Tohoku earthquake and tsunami of 2011. Traditional wooden houses didn't all survive. Many collapsed. Many burned in the fires that inevitably follow when cooking fires and lanterns are overturned. But here's what happened next. They rebuilt. And they could rebuild quickly because of how these houses were designed. Unlike concrete structures, which become piles of useless rubble when they collapse, wooden buildings created salvageable materials. Beams could be reused. Joints could be disassembled, cleaned, and reassembled. Even damaged wood could be repurposed. The community knowledge of how to build still existed. The techniques were alive, practiced by carpenters who learned from masters who learned from their masters. You didn't need to reverse engineer the architecture or wait for specialists. The village carpenters could start rebuilding immediately. Traditional Japanese houses were also relatively quick to construct. Compared to stone or concrete structures, a skilled team could frame a house in weeks. Get the roof on, install the screens, and you had shelter. This rapid reconstruction capability was crucial for survival. When disaster strikes, you need housing now, not in 6 months or a year. The modular, standardized nature of the construction helped too. Pillars and beams followed standard dimensions. Tatami mats, the straw floor mats used in Japanese rooms, came in standard sizes that defined room dimensions. This standardization meant you could source materials quickly and assemble them efficiently. But perhaps most importantly, the house didn't define your life. Because nothing was meant to be permanent, people didn't attach their identity to the building itself. The house was a tool, a shelter, a space for living. If it was destroyed, you grieved the loss, certainly. But then you rebuilt and moved on. Contrast this with cultures where the family home is meant to stand for generations, where bricks might have names carved in them, where the building itself carries immense emotional weight. When such a structure is destroyed, the loss feels permanent, irreplaceable. Japanese culture created a different relationship with architecture, one that acknowledged impermanence and made peace with it. What the modern world forgot. Here's the irony. We've spent the last century building structures that would have seemed impossible to ancient Japanese builders. Skyscrapers that touch the clouds, bridges that span miles, concrete structures that appear invincible. And we've had to relearn the lessons Japan figured out centuries ago. Modern earthquake engineering has come full circle. We now build skyscrapers with flexible frameworks that can sway during earthquakes. We install base isolation systems, essentially letting the building slide on its foundation, exactly like those Japanese pillars on stones. We design sacrificial elements meant to fail first, protecting critical structural components. We even use wooden joinery in high-end construction, recognizing that traditional methods have advantages over modern fasteners in certain applications. But for decades, we forgot. We became so enamored with new materials and rigid engineering that we dismissed traditional methods as primitive. Then the earthquakes came. Modern concrete buildings pancaked, rigid structures shattered, and engineers started asking, how did those old wooden temples survive when our advanced buildings failed? The answer was in the flexibility we'd engineered out of our structures. Japan never forgot because they couldn't afford to. When you have 4 earthquakes a day, you don't get to build experimental structures and hope for the best. You build what works, refine it over centuries, and pass that knowledge down. Now, Japanese construction codes are among the strictest in the world, but they incorporate those ancient principles. Modern Japanese buildings use steel and concrete, yes, but they're designed to flex, to absorb energy, to protect occupants through controlled movement rather than rigid resistance. The International Building Code, used across much of the world, includes provisions directly influenced by Japanese seismic engineering. Base isolation systems, moment-resisting frames, damping systems, all of these have conceptual roots in traditional Japanese architecture. We've added technology, precision, and material science, but the fundamental insight, that flexibility defeats rigidity when the earth moves, came from carpenters working with hand tools and wooden beams. The house that dances. So here we are, 5,000 words into the story of Japanese earthquake architecture. And what have we learned? We've learned that the most elegant solutions are often counterintuitive, that the answer to overwhelming force isn't always greater resistance, that ancient builders working with limited materials and no formal engineering education could develop systems that still impress modern structural engineers. We've learned that good design solves multiple problems simultaneously. The elevated foundation prevents rot and absorbs earthquake energy. The flexible framework provides strength and adaptability. The sacrificial walls allow customization and controlled failure. Every element serves multiple purposes. We've learned that cultural philosophy influences engineering in profound ways. The acceptance of impermanence, the value placed on flexibility, the relationship with nature, all of these abstract concepts manifested as concrete design decisions that literally save lives. But most importantly, we've learned that there are 2 ways to respond to unstoppable force. You can resist. You can build thicker, heavier, stronger. You can anchor yourself in place and declare that you will not move. You can fight. Or you can adapt. You can design systems that absorb energy instead of resisting it. You can build flexibility into your structure. You can accept that movement is inevitable and plan accordingly. You can dance. For centuries, most of the world chose resistance. We built rigid monuments meant to last forever, confident that sufficient mass and strength could overcome any challenge. Japan chose adaptation. They built houses that moved with the earth, accepted disaster as inevitable, and created a culture of rebuilding rather than preservation. And while the rest of the world was building fortresses, Japan was building dancers. When the ground shook, the fortresses crumbled. The dancers survived. This is the lesson of Japanese earthquake architecture, encoded in wooden beams and paper screens, refined through centuries of disaster and reconstruction, preserved in temples rebuilt every generation. The earth will always move. You can't stop it. You can't overpower it. But if you listen to it, understand it, and learn to move with it, you can survive it. While others tried to conquer nature, Japan learned to accompany it. And in that simple shift, from resistance to adaptation, they solved one of engineering's most brutal challenges with nothing but wood, geometry, and wisdom earned through 1,000 tremors. That's the genius of the house that dances with the earth.